In the last lecture, we have studied AVL tree data structure, which can perform search, insert, and delete in order log n time in the workspace. In this lecture, we ask, can we have a data structure which can perform these operations in order one time? And what we will show is that indeed there exists a data structure which is called hash table. Hash table which perform these operations in order one time, but not in worst case but in average case. So these are these three operations. Hash table can perform these operations in average case, whereas this AVL tree performs these operations in the worst case. Okay. Now, what is the idea of hashing? So, the main idea is the hash table is at a fundamental level is an array of some fixed size. Okay, so basically I have an array. I'm calling it the hash table T. It is an array of size, say let's call it H size or size. Okay, and whenever I have a key, so this K key, I have to store this K key. I give this K key to what is called a hash function. And this function is supposed to output an index of this table T, and there we store the key. So that is the basic idea. So this K key can be anything like an integer or a name, or it comes from the key space, the set of all keys that we want to store in the hash table, and we apply a hash function. So this output of a hash function is an integer index in the set 0 to size -1. So for the time being, so hash function simply means a function. We will see that hash function is a function which satisfies some more desirable properties. Okay, so with view of this, let's try to see how the search, insert, and delete operations can be performed. So in an ideal world, so suppose I have a set of keys that I want to store. This is K1 to KL, and for the time being, let's assume that the hash function, so let's call it hash function H, that hash function maps these keys to different indices, HK1, HK2, HKL are all distinct. So this is an assumption. So if this holds, then search, insert and delete is very easy. So here is a hash table, a table which can store keys T indexed from 0 to size -1, and this key1 is stored in the location h of k1, key2 is stored in the location h of key2, and so on. So whenever I have to insert an element ki, I simply apply this hash function h, and if this hash function computing the hash value takes order 1 time, then I know the index from the key ki in order 1 time, and because it is an array, I go to the h of kith index and store the key ki there. So that is the insert. How to search? If I given a key k, and the only place that it can be stored is at h of k, and I look the cell h of k if it is stored there or not. And how to delete? If I am given a key k, I go to I look at the h of k, kth index, and if it is stored there, I simply delete it. So the life is very easy. That all these search, insert and delete can be performed in order 1 worst case time given. So in this case, search, insert, delete takes order 1 time in the worst case. Okay, so this is fine, but we promised, we began with that the hash table can perform these operations in order 1 average case. So why average case? Because of this assumption. This is a big assumption which will not hold most often in the practice. So let us define a terminology called collision. Two keys say k1 and k2. The rest of the lecture is on how can we get rid of this assumption and various tricks if this assumption does not hold, then how we handle search, insert and delete and so on. Okay, and then we'll see that then in the worst case, this time complexity for these operations need not be order 1, it can take more time, but in the average case it takes order 1 time. Okay, so towards that, let's define the terminology called collision. Two keys k1 k2 said to collide under a hash function h if they map into same index, h of k1 equal to h of k2. Okay. So as I said, so if we get rid of this assumption, then in general there can be collisions, and then if there are collisions, then the simple strategy of storing the key ki at the location HKI does not work, because there can be more than one key whose hash value are same. So both of them intend to get stored in the same index, but there is place for only one. So what we need is that, because we have to live with collision, what we need is collision resolution strategy. So there are two prominent line of thought here. First one is what is called open hashing, which is very simple. This is also called separate chaining. So what it is? So look at the hash table. Let's draw the hash table in a vertical manner. So this is my hash table T, and these are the indices 0 to size -1, and at each key what we do is that we have a place to store the key, and then in every table entry there is a pointer, and if there is a collision, then we form a linked list and store the next value here. And so on. So let's take a concrete example. So suppose h of k1 is say 1. Then what I do is that at the first index I store k1, and initially the next pointer is null, and suppose next I want to insert k2, and suppose it collides with k1. So suppose this is also 1. Then what do I do is that I append k2 after k1 and form a linked list, and so on and so on and so forth. So whenever there is a collision, I append in the linked list. Okay, so this thing is called this strategy is called open hashing or separate chaining. And what is the time complexity of, say, search, insert and delete? For example, how would I search? If I have to search for a key k, then what I go in the index h of k, and I need to search in this linked list. Similarly, if I have to insert, I go to if I have to insert a key, say k, I have to go to the index h of k and insert in that linked list. Similarly, delete. To delete k, I go to the index h of k and search for the key in the corresponding linked list and delete from the linked list. So the time complexity of these operations, time complexity of these operations like search, insert delete is order, say order max length, this average worst case time complexity max length of any chain of the chains. So ideally, so this time complexity is less if the length of this each of these chains are less, and when the chains will have short lengths, so when there is less collision, so chains have short length if there is less collision. Okay, so this tells us the required property of hash function. So what is then hash function? Desired properties of hash functions. That there will be the likelihood of the probability of collision of random keys should be less. So the probability of collisions should be less. So that means if I take a set of keys and I apply a hash function, the number of collisions should ideally be less, as small as possible. This take it as a qualitative statement, not a quantitative statement. So or that is the hash function, the hash values should be like random integers in 0 to size -1. Okay. That is one property, and other obvious property is that whenever I have to search or insert or delete, I have to apply the hash function. So computing the hash value should not take more time. So hash values can be computed quickly. Okay. So if these two properties hold, then the hash computing the hash value won't take much time, and the length of individual chains must also be small, and these operations like search, insert, and delete will be efficient. Okay, so here are some examples of hash functions. There is no ideal hash function. For every hash function, you can come up with a set of keys where all the keys collide, because the hash function maps a large domain to a small domain, to these indices, to this set 0 to size -1. So mathematically it doesn't matter what hash function or what function you pick. For any function there always exist, if the size is say L, a big number, then there always exists a subset of size L by size where all these values map to the same key. Okay. So a good hash function is should behave like a random function, and it should not exhibit any pattern. So let's give some examples of some popular hash functions that are used. Not all of them are obviously good. For example, one popular hash function that many people use, which is definitely not good, is h of I. So these hash functions are from set of integers, set of natural numbers to say this set 0 to size minus 1. So if you have I, you define hash value to be I mod size minus 1. This is not a good hash function because it clearly the hash values clearly forms a pattern. Like if you take consecutive values in the domain, the hash values will also be consecutive. So this is sort of one example which is not so good hash function. So another sort of better hash function or better behaving or better looking hash function is called folding. This is what? This is, for example, suppose you want to do a hash function of h of I. What you do is that you write the binary representation of this hash function of this I bn say, and then what you do is that you divide it into blocks of size m. If you need, you do padding, and then you take logical AND or logical XOR of these parts. So suppose this is say part 1, this is part 2, and so on. So you define hash function h of I to be p1 say XOR p2 of these values, and to respect the size, what you do is that these values, whatever the value becomes, you take mod size minus 1. So clearly this hash function looks much more random than the first hash function, and so on. So in any textbook you will find various random looking hash functions that are typically used, but as I said, so there is no sort of the best hash function. So depending on the application, you have to try, like it should behave as randomly as possible. Take this statement as a qualitative statement, not like a formal statement. Okay, so that is what is called open hashing. The second strategy is what is called closed hashing. So open hashing is what? Open hashing is you attach linked list to each cell, so that particular strategy, and that's how you resolve collision. That is called open hashing or separate chaining. The second one is called closed hashing. And this is also called open addressing. So in this case, the one drawback of separate chaining is that it involves pointers, and typically if your operations require pointers, then that tends to become slow because your memory access can be all over the place. So recall what is array. Array is a contiguous piece of memory, and in a computer memory, where if you access consecutive cells or consecutive memory addresses, the access will be much faster than if you do a random access. Okay. So here is your hash table T, and what open addressing does is that it uses some more hash function. So let me write it first. So suppose I am given a key k, and then what I do is that I have a hash function h of k, and I first look at this cell. If this cell is empty, then my life is good, life is very okay, and I simply store the key k. But if this key k is if this cell h of k is not empty, or there is already some key residing in the place h of k, then what I do is that I look for a sequence of places. So this is called h. So this hash function, write this way. So this hash function takes two arguments. The first one is from natural numbers, and the second one is a key. So first I try h0k, and if this cell is empty, then I try h1k, which may be this cell, and I check whether this cell is empty or not. If this cell is empty, I store k, and I am done. My insert operation is finished. If this cell is also occupied, then I look at h2k, and so on. So these are the consecutive tries, and that's what closed hashing or open addressing is. So what is the insert subroutine? How does insert subroutine work? Suppose I have to insert a key k. I look at first h0k, and if the cell is empty, I store k here, and I am done. If some element has already occupied the cell, I look at h1k, and the cell at h1k, and if that cell is empty, then I store my key at that cell, and I am done. If that cell is also occupied by some other keys, then I look at h2k, and so on and so forth. I continue my search when and when do I stop? When I find a first empty cell. So that is the insert. How is the search? Again, the search is that suppose you have to find whether the key k is present or not. You can't simply look at h0k. You have to continue your search till you find an empty cell, or there is something called dirty cell. So so first you search for h0k. If it is present here, then you have found it. Otherwise, if this cell is empty, then you report that you have not found it, and if this cell is already occupied by some other key, then you can't terminate your search. Obviously, you have to search at the location h1k, and if that cell is again occupied by some other key, you have to search for h2k, and so on and so forth. So what are these functions? So typically this hik, this function is one popular choice is you take a hash function h, so let's call it h prime, and what you do is that you simply add I, and then to respect the size you write mod size. So what this function basically does is that the hash table T, and it first tries to insert the key k in this index h prime of k, then what it does is that it simply does a linear scan. What is h1 of k? It is nothing but this is h prime k plus 1. So it simply searches for an empty space in consecutive cells, and whenever it finds an empty cell, it just simply puts it there. Okay, so this particular case is what is called linear probing. We probe the consecutive cells linearly. This is called linear probing. So one good thing about linear probing is that if there is any empty space in the table, if there is any empty space in the table, then insert will be successful. Okay. On the other hand, a bad thing is once a chunk, once a part of table gets occupied, this is called primary clustering, then when a new key is getting to be inserted, then if this hash value is randomly spread over all the indices, then if this is some cluster has formed, then it becomes more and more likely that this new key also end up in this cluster, and not only that, it will finally get inserted at the end of the cluster. So that degrades the performance substantially. That means subsequent inserts are more likely to land into this primary cluster that has formed, and not only that, it will make the situation worse and worse. It will increase the size of the primary cluster, and the next insert is likely to be more expensive, and so on. Okay, so this is the problem of linear probing. So obviously, what is the solution? So there is some problem with this thing, that don't search linearly, search more like random. So the idea of quadratic probing comes from here. Quadratic probing. Don't probe linearly, probe quadratically. That means what? That means h of I and k is h prime of k. You apply the hash function, and you add I square, and then of course, to respect the size of the table, you do mod size. So this is called quadratic probing. Good thing is that it avoids primary clustering. Okay, but it has some more fundamental problem. A more fundamental problem is that the insert may fail even if the table has lot of empty spaces. It may happen. So let me write here. insert may fail even if table is half full. Table is half full. And the situation can be worse if you take arbitrary, if you don't take table size judiciously, which we will talk about just now. Then it does not need to be half full even. It can be say 90% empty and still you may not find the insert may fail. Now what do you mean by insert is failing? I mean that when suppose you want to insert EK, you look at H0K and suppose this is this cell, and suppose there is already some key is present there, and then you go H1K. Suppose this key is present there, and these are the consecutive cells that you are doing, and suppose H2K, and suppose this again H3K. That means the cells that you are probing may form a cycle, and once it forms a cycle, then because of this function plus I square, then H4K will be H1K and so on. Then it does not matter how much you try, you won't find an empty space, empty cell for this key. Okay, that's what we say, that the insert will fail even if the table is half full, or it is even 90% full if you don't take size properly, table size properly. Now what do you mean by taking table size properly? We formally mean this, that if size is prime, size is a prime number, then insert always succeeds if the table is at least half empty. So let's prove it. What we basically need to show is that if the number of empty cells is at least size by 2, then this cyclic thing cannot happen. Okay, so let's see. So suppose these cyclic things happens, and I look at say H0K to till HIK till say HJK. These are all distinct places, distinct cells, and I'm searching for an empty cell while inserting K, and these are all distinct cells, and all these cells are already occupied. And suppose this is equal to HIK. Okay, that means what? That means I have already seen J many distinct elements. I've already seen J. So let me write properly. The number of elements in, so that implies that the number of elements in T is at least least j, and in particular we have j is less than size by 2, because if j is more than size by 2, that means there are more than size by 2 elements in the table, so it's less than equal to, which is a contradiction. We assume that the table is half empty, the number of elements in the table is at most size by 2, so in particular j is at most size by 2. Okay, now you are saying that hjk is same as hik, and let's see, and we will prove that this leads to a contradiction. So let's write here hjk is equal to hik. Now what does that mean? That means h prime k plus j square equal to h prime I plus h prime k plus I square mod size. So this h prime k gets cancelled, and what I get is j square minus I square equal to is congruent to 0 mod size. Now what do I get? This is j minus I times j plus I is congruent to 0 mod size, but j not equal to I, so this is not equal to 0, and j plus I is j is less than equal to size by 2, and I is strictly less than j, that means I is strictly less than size by 2, so this is strictly less than size and greater than 0. Okay, because j is greater than 0, j is at least 1, so that is a contradiction. So this is not equal to 0, and this is j plus I is some integer strictly in between 0, strictly in between say 1 and size minus 1, and their product hence can't be, so this product is not divisible by size, because size is a prime number. Okay, so that concludes the proof that if there is if the table is at least half full, then this secondary clustering will definitely find an empty space. Okay, and the third technique is what is called double hashing. What is double hashing? It is again very easy. So what you do is that you define h I comma k is, you take two hash functions and you define say h1 of k plus I times h2 of k. Okay, and you try the consecutive sets. Okay, so all this is good. So in hashing, an important terminology is what is called load factor. So load factor is what is the number of load factor, or simply load, number of elements in the hash table T by size. Load factor or simply load is also called load, and this is typically denoted by lambda. Now typically this lambda value should be small, so ideally this hash table should not be too full. Otherwise it does not matter what you take, how good a hash function you take, or whether you are doing open addressing, open hashing or closed hashing. It does not matter, the performance will be much bad. And the thumb rule is that ideally this lambda should be less than half. If lambda is less than half, that means that if you are using quadratic probing, you will find empty space and so on. So when you are doing insert, delete, you keep track of this lambda, and when lambda becomes more than half, or you see that the insert or the search operations are taking too long time, then what we do is we perform rehashing. What is rehashing? Typically you take a bigger table size, a thumb rule is you double your table size, and you pick new hash functions. Okay, you pick new hash functions and you discard the old hash table and build new hash table. Okay, so that is the rehashing operations when your hash table becomes too loaded and it has become inefficient because of load. Then you perform this rehashing, but remember this rehashing is a very costly operation. You are again building your hash table from scratch. So this you do when the performance has really degraded, or the table has become loaded, its load factor has exceeded half, and then you can do rehashing. Okay.